So what I'm going to describe is work that I did quite a long time ago, but I thought that it was going to be useful for students mainly. The question concerns out of equilibrium systems, so systems that are driven out of equilibrium. Now, what you have to bear in mind is that what things do we know? First of all, what things do we know about equilibrium? Do we know how to solve a given problem? And the answer is no. Almost no problem can be solved. We have the Gibbs measure. We're told that things in equilibrium can have a probability that is proportional to this. But of course, we don't know in practice how to calculate this for almost any model, except for a very few exceptions. But the thing is that this already tells us a lot of things about how the system is. It will tell us that it will want to make its energy low, but it will want to make, at the same time, its entropy large. We know a certain number of things that happen to it, even before we start solving the problem. How do we get here? Well, you remember that when we study StatMech, we start by, first of all, saying that energy is conserved in an equilibrium system. And then, first of all, we are taught that if we choose a point with a flat measure completely at random on the energy shell, Liouville's theorem tells us, classical mechanics tells us, that after some time, after any time, the distribution continues to be flat and random. So that if for some reason the system already has the same probability of being in any point on the energy shell, it will continue to satisfy this. Of course, we don't know that it has started this way, and this is an extremely hard subject. It's a subject of ergodic theory, to say, how do I get to such a situation? But at least classical mechanics guarantees that if I got there, I stay there. So one part of StatMech, which you usually don't do, is usually in the first few pages of the book, they tell you, well, you know, these things in a big system, because the trajectory is so chaotic, it will be as if you have a flat measure, and then you stop thinking and you make an act of faith, and from here onwards you compute things as if you had a flat measure. Of course, once you have it, you stay there. From here, remember what you do. You break the system into pieces. You say that the interaction between the pieces is small, and you end up with saying that this is also as good as saying a flat measure, and you do the one you choose. Okay. So there is another method, another thing you could do, and it's even much simpler, is to put your system in contact with a thermal bath. For example, a bunch of many oscillators with the right energy, and then it is and then you say that those oscillators, which are the bath, those are chosen randomly with the appropriate energy, and then it is very easy to show that the system, thanks to the thermal bath, I'm going to make it more clear what a thermal bath is, will explore this. Okay, what do we know out of equilibrium? Out of equilibrium, as I'm going to show you, you could, and I'm going to show you how, fix the energy. So, for example, you have a bar that is conducting heat. You could fix the energy and keep it at a given value. This will happen more or less naturally, or at least in the thermodynamic limit naturally, but you can also impose it. But then you don't know that this surface of energy is going to be explored uniformly. You know that generically it will not. And so what do you know? I mean, what do you gain by fixing the energy? Well, really nothing from the point of view of calculation or of your knowledge. Because, for example, and I'm going to give you a concrete example, the system could stay in a very tiny portion of all this thing, and that would be it. By the way, many years ago, Mr. Janes proposed precisely that we take averages flatly over some surface of energy plus other constants that we fix, and he proposed this as a method to do out of equilibrium. Of course, it does not work, but it has had a recent resurrection. Okay, so now one of the very, very few things that we know out of equilibrium are the fluctuation theorems that have been going on for now, I think, 25 years. So what is a fluctuation theorem? So you get your system, and you can decide how you're going to start it. One possibility is to start it in equilibrium at temperature T. Another possibility we will see in a minute. At that time, you begin to apply some work to it. For example, stirring it continuously, and you do this for a time t. And then at time t I stop and I measure how much did it cost me to do in work, no? And then I start the experiment, exactly the same experiment again and again and again. And of course, this quantity fluctuates a little bit, because imagine there were 3 molecules. Well, they will hit against these I don't know what's the word, in different manners, and you could spend a little bit more or a bit less energy. So you build a histogram of how much it cost you the work divided by the time. Big T here, unfortunately, is the time. Or, no, it's a temperature, it's okay. And you do the histogram, and you get some curve like this, which has, now, if the system is big, this is going to be very peaked. And of course, almost always you do work to the system, and this is the second principle. Normally, when you stir coffee, it's very rare that the molecules of coffee arrange themselves to give energy to your spoon, but this could happen. I mean, it's extremely unlikely, and the bigger the coffee cup, the worse it's going to be. So what the fluctuation theorem says is that when you look at this histogram and you compare not around the peak value, that would be nicer, but unfortunately it's not true, around 0, which is much less interesting. If you do the probability of doing some work and you divide it by the probability of doing minus that work, this thing is just an exponential for whatever system and under almost no conditions. So, in other words, if I take the log of this curve and I do a Taylor development around 0, the odd part is only linear. This is an extremely strong result, and this, I will say, under which conditions. So, at time t, you do the probability of the work, and the fluctuation theorem concerns that. Of course, you could have started, there is another version of the theorem in which you turn this spoon on, and you want to keep it forever working, and you want to not start from equilibrium, but start from a situation that is stationary. But already there you have a problem. How can you have something stationary if you're doing work on it? It's not possible. It will typically warm up. So what you need to do is you are obliged, in that case, to connect to a thermal reservoir that will take the heat away. If you do that, you turn this on, you make it work for 15 days, and then at time 0 you start measuring, and you measure up to time t, and you do the same thing. And now the same theorem, which was true always, 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 is going to be true too, but under more restricted conditions. And here is where the story starts. Yes? Sorry? Here? Oh. Yeah, yeah, sorry, yes. It's interesting. Small t is the temperature and big T is the time or something like that. Yes, sorry. It's the work. So you want something here that is the total work and it's not divided by the time. And this T, sorry, is, you wouldn't put it. Okay, so there are several conditions of this theorem. This was a result that was more or less guessed and more or less proven in some cases by Evans, Cohen, Morris. Then Gallavotti and Cohen proved it in a version that I will come back to, and then it was proven in many other sources. Because the theorem, the one that says this relation, is so widely general, there was a lot of experimental work subsequent to this, and you could ask, what was the experiment testing? If a theorem is almost trivially true, you may wonder what an experiment exactly is testing. Okay, so let us start with a thermal bath. What kind of bath can I use? So one possibility for a bath is to have, up to here you have just Hamilton's equation. Let's say that we have a normal kinetic energy, so the velocity is velocity. And now here we have the force, the acceleration has a gradient term. We have a driven system, so it means that we need a force that does not derive from a potential. That is what driven means. Some of the forces do work. So we have some driven, and because of the reason I was mentioning, you need a thermal bath. Now, a stochastic thermal bath is you add a bit of friction, proportional to the velocity, and you add noise. And this is just the Langevin equation with inertia. So you have a Hamiltonian system that is being forced. It would heat up forever if it was forced. So we add friction and we add noise, in a way with a relation between noise and friction that keeps the right temperature. So as I was mentioning before, when you have such kind of bath, there is no problem with ergodicity. The system doesn't stay trapped in a region of phase space because you have always a finite probability that the noise will take you anywhere else. Now, in that case, as I will say in a second, the fluctuation theorem is trivially true. And it's really a two-line calculation to prove it. Now, traditionally, people who do simulations had introduced another kind of thermostat that keeps the system, even when you drive it, at constant energy. It's called a Hoover thermostat, and it is not something you can implement in real life. Nothing in real life resembles this. So you're going to force the system, but at the same time, you're going to keep the energy constant. You might think that if I drive a system and I keep the energy constant, I'm doing nothing. It's not true, and you will see now an example where very clearly you keep the energy constant, you drive the system, and you get something very different. Okay, so how do you do this? It's very easy. You do the same. You have Hamilton's equation, you have a friction, you have your forcing that you're applying, but now, instead of adding noise, you just change the amount of friction, you tune it at each time so that the energy is constant. It's very, very easy to show that the energy stays constant if you adjust your friction at each time with this formula between the force and the velocity. So clearly, you're not allowing the system to grab any energy because you are at each time putting exactly the right friction it takes. Notice that there is no noise. So if the system started for some reason in one region of phase space and there is another region, this is the energy shell, and both are possible, but there is no path that joins these two, with this thermostat you're not going to make it. While the stochastic one will, because you have always a non-zero probability that the noise will take you to the other side. So all the questions, if you want to prove something with this thermostat, are going to be mathematically very, very hard, because you are back with all your problems of ergodicity. Asking the question, is my deterministic system going to explore all its possibilities or not, is an extremely tough mathematical question always. Yeah. Yeah. But this happens presumably for a small time, yeah. But it's, in any case, this is practical, in fact. It never, I mean, you put it in a computer and it works. It works, yeah. You might wonder why they wanted to use this thermostat, and it was long before these things were applied to mathematical physics, they were already popular in simulations. Well, no, of course, thermodynamically, this is extremely rare for a macroscopic system, but it could happen, I mean, in 2 dimensions, at isolated points. Yeah, sure. Thermodynamically, it's extremely unlikely. Okay, you could do something in between. You do the same idea, the same Hoover thermostat, but add some noise. But now the noise, you keep it from taking you out of the energy shell. In exactly the same way, you use a noise that is tangential to the energy surface, or if it is not, you project it onto the energy surface. So now everything will be okay. If the system naturally had 2 attractors, let's say, you could always have a chance that the noise will take you from one to the other. This before you take the thermodynamic limit. In the thermodynamic limit, then the story is harder. But you will always have something that takes you, and the questions of ergodicity don't matter. Notice that I'm talking of ergodicity. What I call ergodicity is the possibility of visiting every possible trajectory, and not the fact of exploring flatly, which you don't do. So in this case, both in this case and in the previous case, if you're forcing your system, you're not exploring your energy surface democratically as in equilibrium. And I will give you an example that will make this perfectly clear. Okay, so at what conditions does this famous fluctuation theorem work? It depends on the initial condition. If the initial condition is in equilibrium, as I told you, it is trivial to show that it's always true with no assumptions. You measure the work at any time, during any time, repeat the experiment, compute the histogram, and the fluctuation theorem is always true. Now, what about the stationary initial conditions? The stationary initial conditions means that I turned on the system a week before, let it work, but of course for this I need a thermostat, because if not the system in a week will heat up. So I apply a thermostat, and let's discuss which thermostat in a second, but at time 0, after a week of becoming stationary, I measure the work, and now things are a bit more subtle. If the thermostat was stochastic, so if the thermostat is this one, this is still a thermostat that keeps the energy constant, then again it is trivially true. But if it is this thermostat that doesn't guarantee, it only guarantees that you keep on the energy shell, then you need to say something about the nature of the system. And here is where the whole thing, the whole problem with mathematics started. It is a historical accident that, at least in Europe, this fluctuation theorem became known in this version with this thermostat, and this is where Gallavotti and Cohen proved what are the conditions on the dynamic system so that the theorem is valid. So over an entire field of which 99% of the result is trivial, they managed to put the finger in the angle that was really hard. And his paper, their paper, is really hard. Okay, so they proved that the fluctuation theorem, in the case where the thermostat is purely deterministic is true, provided the system has certain properties which means that they are it is as chaotic as it can possibly be. So the theorem asks of the system to be Anosov, transitive. I'm not going to define these things. This is just means something with respect to the stability of orbits. It's something very much of the nature of the system as a dynamical system. You are asking it to be as chaotic as you can possibly be. How many systems can you prove are of this kind? Two, I think. You normally cannot prove that because it's an extremely hard thing to ask. So what Gallavotti did later, and this is an important point, he said, okay, but just in the same way, can't I make a virtue of necessity? I don't know how to prove if if any system is really of this kind, but can't I use this to begin to reason, just as when as I mentioned before, the first 3 pages in a StatMech book tells you about ergodicity. Can't I use this as a path to follow in the following way? I will postulate that a system that is macroscopic is as if it had all the properties needed of chaoticity so that the fluctuation theorem is true. So instead of proving it, he is using it as a postulate. And he says this postulate, which is he calls it chaotic hypothesis, and it's inspired on something similar that Rel had done in Spirit. He postulates this as a way to go. So you are postulating that ordinary systems of ordinary life that are out of equilibrium have this incredibly subtle and impossible to prove mathematical property. But once you postulate it, then you can follow from that point. So, funnily enough, Gallavotti chose the hardest end of a relatively trivial field, trivial in the sense of simple from the point of view of proofs, and made an incredibly hard theorem that makes incredibly impossible to prove assumptions in most cases. But of this, which is a drawback, he took some ideology that then was used or is interesting to discuss the problems out of equilibrium. So let me give you an example of where the theorem, the way Gallavotti and Cohen postulated, doesn't work, meaning that the theorem is okay, but the hypotheses are not valid. So we consider a box, and we add an electric field pointing downwards. We push the particles. At the same time, we apply a thermostat, the one I mentioned before. So what does a thermostat do to a particle that is being pulled by a field? It keeps the modulus constant. I mean, this is its job. So I apply the formula with a gamma I showed you before, and what you get in a line is this. So you have the ordinary p dot x, sorry, now it's x, that is being pulled from you, but then you apply the extra term, and you apply it in such a way that it conserves the momentum. So in words, what's going on is that if the particle is moving like this, it is being pulled down by the field, but the thermostat keeps its modulus constant. So what in fact happens is that it changes direction. The field sort of aligns it, wants to make it go in its direction, but the speed doesn't, the modulus of the speed doesn't increase because of the thermostat. So a trajectory that is like this will sort of align, and a trajectory that was going against the field does some kind of parabolic thing. If you write the equations for this silly example, what you get is that the angle is exactly the angle of a pendulum. It's exactly like in the case of the Hamiltonian of a pendulum. It wants to be down. If it's up, the angulum swings back down to zero. An overdamped pendulum. No, yeah. So rapidly it converges. This is an acceptable case. I am forcing a particle. I want to see if the fluctuation theorem works. But let me on top of it add a little bit of noise. As I said before, I added a bit of noise in the game. And then what you see, what you can prove, and it's very easy, is that what you get is that this angle has two possibilities. Already without noise, this possibility going upwards is a stationary point, because when you go upwards, just as in a pendulum, the upper position is allowed. The modulus is conserved, the dynamics is okay, there is no problem. If I had a little bit twisted the angle, then it would fall in the other direction. So there are two possibilities that are stationary. One is called the attractor, which is the one all trajectories want to go to. And there is an unstable one, so unstable but stationary, which is the repeller, which is like being up. So the situation exactly in this case of this force system is like a pendulum with or without a little bit of noise, but with two situations. So now you can do the calculation, what happens to a pendulum that is under a little bit of noise. And what you see is that the pendulum in fact switches from being in an equilibrium position. Then very occasionally it makes an excursion to the upper position where it spends some time, and then it goes down. And it switches between being parallel and anti-parallel. This is a simple calculation too. All intermediate situations are fast and don't count in the long term. And now if you look at how much energy you spend, in this case you're giving energy to the system, in this case he is giving it to you, so you have times where anti-parallel where to the field where the system gives to you, times where it does not, and then when you do the quotient, you get that indeed the fluctuation theorem works. So if you have a little bit of noise and your particle in the example I gave has the time to explore the parallel and the anti-parallel situation, then everything is okay and the fluctuation theorem works. Now imagine that I do the same thing without noise. Now, without noise, what happens is exactly what happens in a pendulum if you have no noise. You have just the deterministic dynamics, overdamped dynamics. Simply, you never go from one situation to the other. So, if you start it like this and you have no noise, you will never fall. And if you start it like this and you have no noise, you will never climb. It is this passage that needs a little bit of noise. So in the picture I made of the energy shell, there is one attractor, which is going together with the field, and there is one, this call it attractor, this is called a repeller, which is you are going opposite to the field. This is responsible for a positive amount of power. You are giving power to the system, and this, much less likely, is responsible to the negative one. The fluctuation theorem relates these two, but the problem you have is that if you don't have any noise, you just have the deterministic thermostats, all points flow to this one, and here, and you never commute between the two. So this can be made exact, this statement, and what you discover is that attractor and repeller are indeed divorced unless you add a little bit of noise. And this is the essence of, this is clearly an example where with a deterministic thermostat the fluctuation theorem doesn't work. This is the kind of problem that specifically Gallavotti proposed that we exclude, that we consider that realistic systems don't do. So let us be a bit less trivial. So this is the same problem, but now we have a Sinai billiard. We put obstacles. This is perhaps one of the only systems where you can, in the Hamiltonian case, when you don't drive it, prove something. And it's hard. I think it was Sinai, no? I mean, it's a big thing of ergodic theory. You can prove everything for this case without driving. And you can now drive it. So for this case, it's interesting that you can understand very well what happens. So this is a system where, when the driving is small, both it is completely ergodic. So the energy shell is completely full. So, sorry, I get a choke somewhere. Yeah. So in this system, when E is 0, we are fortunate, we are told by Mr. Sinai that the energy shell is completely well explored. Perfect. Now, this very same system, we're going to start cranking up the field. What happens? Well, let us first go to the extreme case. We are cranking it really hard. If we crank it really hard, you see what happens. The particles here, now it's a bit like the free system. It wants to align with the field. It bounces, but it does a little bounce, and then because the field is hard, it aligns again. And then blip, 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 blip. It goes down up to here. Then blip, blip, blip. It jumps, and then re-enters here. And you see that this is a perfectly good trajectory with very strong field, and this is by no means ergodic. It's not exploring all the possibilities. There are many other trajectories here. So there will be another one here, but there are many that you're not exploring. So we know that for E much larger than 0, we are in the divorce case with an attractor and a repeller, only that the attractor is now a bit more complicated. You see, it's not just a silly trajectory as in the free case, it is really a nasty thing with many bounces. Still, the fluctuation theorem needs that you are able to do excursions back and forth, because this one is giving you the negative peak of this other one, and you're not. Let me tell you, you might think, who's the attractor and who's the repeller? This is a tricky thing. This one is the attractor, and the repeller looks the same. It's the same trajectory pointing upwards. But notice that you're not supposed to look things in configuration space. You have to think of them in phase space. In phase space, this one going down and this one going up are in different places because they have opposite p's, let's say. So attractor and repeller, although they look the same in real space, they are not. They are divorced. So this is a case where the fluctuation theorem without noise fails, and this illustrates what is the assumption that Gallavotti and Cohen were making. They were making the assumption that this kind of situation does not arise in real life for a macroscopic system. The idea is that the idea is that an intermediate situation where you force a little bit, you get an intermediate situation where attractor and repeller see each other. Actually, you can, this is exactly what happens. For moderate driving, you have a way that attractor and repeller are intertwined, and you do have a fluctuation theorem, but when the field gets big enough, then what happens? And what is it that happens that makes the theorem not work? It's simply that the time of passage between anti-parallel and parallel, now it's a little bit more complicated with all the bounces, becomes, this time, these jumps become extremely rare. So notice that this is the same as when you do Ising model in one dimension, where you have two possible states. If you go to very low temperature, the wall between up and down begins to be very expensive, and your sample might not be big enough to contain a wall. So the equilibrium of up and down is lost because just one wall is too expensive. Here expensive is, what is the expensive in what? In the probability of going from one to the other. Yeah. 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 I don't think that nothing is known on that. I don't think that anything is known. What I showed is how to calculate, when you are in a divorce situation, the instanton contribution. So this I'm going to arrive in a second. But still, for that you need to know lots of things about the dynamics. In other words, to put it in jargon, you don't know how to calculate your instanton. But I don't think this is known for any system. Now, perhaps the more knowledgeable colleagues here will correct me, but I don't think this is known for anything. Perhaps you, Kiron, you didn't do work on this? If we know of some case where we exactly know when attractor and repellers divorce, I'm not aware of anything. It's hard in any case, that's for sure. Okay, so now you can add a little bit of noise and ask yourself what happens. Well, it is not hard to see that a little bit of noise immediately cures the problem. You are in your attractor, but you have a very tiny chance that noise will manage to make you go up. And then you might be very lucky. You can do this more precisely mathematical, but then you can be very lucky and that noise takes you to this situation or to something that, as people in dynamic systems say, shadows this situation for some time, and then, bada-boom, it falls back. So even in this case, noise will give you a chance to go back and forth, and again, the theorem is trivial. So what is, so here you have the picture I did in the board. So in conclusion, the fluctuation theorem is not only a test of ergodicity in an attractor. Within the attractor, you can move and explore everything you have. But still, you need to be able to pay yourself a trip to the repeller, which is unstable, and then come back. And for a driven system, this is not guaranteed. So the chaotic hypothesis is basically putting yourself in conditions such that the fluctuation theorem works. It's saying that real systems are such that for all practical purposes, the fluctuation theorem works. And so what is it that you're postulating? You're postulating that your system manages to visit everything that is visitable. Every place where the system can have dynamics, it has to be able to visit. But not only every system within the attractor, which would be normal, but every place within unstable points, which is the repeller. The fluctuation theorem needs you to go to the repeller. This is an extremely strange condition because you're asking for a system to have a tiny probability of doing exactly the reverse of what it normally does for some time and then coming back. And in the case of a macroscopic system, you're asking that this might happen in the macroscopic limit, which is even harder. Okay, so the original setting was, because they knew mathematically to prove that this happens, that you can pay yourself, that attractor and repeller are not divorced if your system is Anosov and transitive, which means for us very, very chaotic in a very mathematically precise way, something that you cannot prove for almost any system. So the idea is that you assume it, and this is your chaotic principle that would guide you. But notice that for the same price, you could, or maybe not for the same price, but you can make also the assumption that your system is such that if you add a little bit of noise, nothing is going to dramatically change. Now, if you add a bit of noise, fluctuation theorems are automatically true. You're always going to be able to visit attractor and repeller. To close the loop, and this is, I think, why I wanted to give you this talk, is that some of these properties of being axiom A, transitive, etc., these very mathematical properties of dynamic systems are defined by adding noise and taking them to zero. The person who has done more work on this is called stochastic stability. You add something stochastic and take it away, and you ask that the limit of zero stochasticity is a good limit, it's a real life. So stochastic stability has been used to define axiom A and all these other very technical things. So what I think, but I'm not mathematically powerful to prove, enough to prove, is that it is possible that, in fact, all the assumptions of the chaotic principle could be replaced simply by saying you will assume that your big macroscopic systems are stable with respect to adding a little bit of noise. And that is an assumption that for a physicist is much more digestible. So, thank you very much.
Any questions? I check.
So two questions. So one is when you change the electric field, I mean, is it a sharp transition, or is it like, you asked the same question? Is it
and you know, the problem, what I tried to prove is that I proved what was the price to go from one place to the other. Oops, sorry. So, no, I don't know, and especially because if the price is exponential to go from one to the other, things are relatively controllable. You calculate a trajectory, the log of its probability. But if it's power law on top of it, it could be that they touch in some fractal set that makes the passage just power law in the noise. And then I don't see even how you would come about to do it. But I don't think it's too hard, I think. I don't even know numerical cases that have been done.
Okay, the other question is, so these fluctuation theorems are, when it's valid, these are the transient ones or the stationary?
No, these are all for the stationary ones, but the stationary is bad in the sense, what is bad is the stationarity you arrive in the sense that it's not exploring everything. For the ones where you start in equilibrium, you already have a slight probability of having started on top and on the bottom, so you don't need to pay yourself the trip between attractor and repeller because you already a good fraction of the time started in one and in the other. So for the one that starts in equilibrium, the transient one, everything is okay, always.
Somehow this stochastic stability must be in a sort of the strong sense that because, well, the measure will still sort of sit on the attractor in the limit. So when the noise is very weak, you will almost not see this.
The stochastic stability would be with respect to validating the fluctuation theorem. The measure, of course, is not a good enough measure. Yeah, sure.
So that sort of in another systems that sort of assured by this sort of wandering transitivity type assumption.
Is not. You should say that you have it with noise, and then when you take noise away, it stays.
That's sort of usually a consequence of the assumptions for another.
Yeah.
You wanted to invert a little bit,
But for example, one of the things that Anosov gives you is the existence of an SRB measure. Now, sometimes it is introduced as a stochastic limit, no, going to zero.
Yeah, but
if I understand correctly the papers.
But then it wouldn't. You need a little bit more to have this.
For the measure, you're right. If it is for what is the measure, if it is for how the measure is reached, then that would be okay. Yeah. But if it's for, yeah, you're right. If it's only the nature of the attractor I'm worried about, that's not enough. But that's another, and that is a mistake in the papers of Gallavotti and Co. And they, en passant, they say, well, the longest time of a system is the eddy return time in turbulence. No, not at all. The time to go to the repeller and come back is way much longer than the eddy return time. It has to do with Avogadro's number, not so that's clearly a mistake. Everything that is physical is in the attractor, of course, as you say.
Like nothing changes dramatically from small noise to no noise. Small noise, small with respect to what?
Well, it has to be a limit, and there will be some quantity in the system that will tell you, in fact, any number is okay, because time will scale with the amplitude of the noise, unless there is a thermodynamic limit intervening, and then you have a problem between the commutation of large n and small noise, and you have to decide, small with respect to the size, how it goes. But if a system is 2 degrees of freedom and you add any amount of noise, then with some price that is finite for that noise, you go to the other side. So in that case, it's small with respect to the time of observation, of course, but that you're sending to infinity.
Other questions? If not, let's take Jorge again.